Swayam Prabha. Digital India. Educated India.
Welcome to this course on transition metal organometallics in catalysis and biology. We have been discussing a very important topic which is a Nobel Prize award winning topic, olefin polymerization, in the past few lectures. In this regard, we have approached this topic from two perspectives. To start with, we have looked into it from the perspective of application point of view. Particularly, we started talking about polymer classification from the application perspective, and we had spoken about various kinds of polymers like thermoplast, plastic, duroplast, elastomers, elastoplastic materials or thermoplastic elastomers and reversible duroplasts. So, these were all classified based on the properties of the polymer. Then in the same topic we have looked into polymer classification based on the chemistry perspective, from a chemistry perspective based on the process in which by which they are synthesized, and in this context we have looked at two kinds of classification. One is condensation polymerization, the other is addition polymerization, depending on the reaction by which they are formed. For example, if they use a condensation reaction where a small molecule is eliminated as a path to polymerization, then these are condensation polymers, whereas when the monomers are just added without elimination of any a molecule, they are called addition polymers. And for one main feature of addition polymer is that the composition of the monomer and the composition of the repeat unit of the polymer are the same, they are constant. So, we have done that, and again we have also looked into the classification of polymer from the perspective of the mechanism point of view, and these were from the mechanism by which these polymers are formed. In this context, these polymers can be divided into two types based on the pathways they take. One is step growth polymerization, the other is chain growth polymerization. And we had seen what are their characteristic molecular weight profile of the polymers so formed in this process as a function of % conversion of the reaction, polymerization reaction. And what we had seen that that in the step growth process, the molecular weight sort of increases drastically, significantly towards the end of the polymerization, that is towards the end of at higher % conversion, whereas molecular weight does not have a bearing in case of chain growth polymerization on % of the conversion of the polymerization reaction. So, in this context we have also discussed about the various types of polyethylene which are obtained and the types of processes which are synthesized, and polyethylenes are of three types based on their densities. The first one is LDPE. These are synthesized by these are called low density polyethylene. Polyethylene can be classified into three parts. The first is the LDPE or low density polyethylene. The next one is HDPE or high density polyethylene. And the other one maybe I write it later. The next one after low density polyethylene is LLLDPE, this is linear and then is HDP is high density polyethylene. Or HDPE. This is there are three types of polyethylene. Depending on the branching, this polyethylene has different material properties. Some are soft, some are hard and brittle, some are transparent, some are opaque. Now, in the last class we have also discussed about the industrial processes that are used for preparing these kind of polyethylenes, and the first one that we had spoken about was this ICI, Imperial Chemical Industries. First developed this process for preparing LDP, linear low density propylene, in 1993. So, this is probably the oldest polyethylene polymer to have been prepared industrially, and presently these LDP are prepared radical polymerization using oxygen initiators. So, like peroxo compound. Now, these radical polymerization is not good because it has several limitations. Requires high pressure of around 2800 bar. So, and also the reaction is uncontrolled. As a result, polyethylene obtained are branched, has significant branching, and they are soft material without non-crystallinity. So, the next process or the process which is used for preparing high density polyethylene HDPE is the Phillips process. This was discovered by Hogan in 1956, and this is used for making this high density polyethylene, and it was using chromium trioxide as the catalyst and pre-catalyst as the pre-catalyst. But the real the chemistry was done and this was done on a heterogeneous fashion. Heterogeneous fashion on silica surface. Done on a heterogeneous fashion in a silica surface. Okay. So, these Phillips process actually uses chromium 2 and chromium 4 as the active metal centers which carry out this polymerization process. We have also seen that improvement of the Phillips process was reported by Union Carbide. Union Carbide, which use chromosine. which is chromosin low valent chromium compound as the precursor for this HDPE. Now, there is another variant of the Philip process which uses hydrogen to control the chain length. So, chain length under Philip process chain length of the Philip process is controlled by metered addition of hydrogen chain length of is controlled under metered addition of hydrogen and that sort of gives rise to this low density polymer, and this is how this LLDP is produced. Now, in context of this there was a significant discovery which is another process called unipole process. Unipole process from union carbide which uses fluid bed reactor. And they have been used for producing both LLDP as well as HDPE. So, this is an interesting process. So, what we see if we sum up that there are several industrial processes involved for producing various grades of polyethylene. To start with, it was the ICI or Imperial Chemical Industries. Currently, also radical polymerization is used with oxygen initiators for producing LDP, low density polyethylene. For HDPE, it was a heterogeneous chromium trioxide process in 50s called Philip process, which was producing HDPE, and then union carbide comes into play and produces HDPE with chromosin, which is a low valent chromium precursor, and finally, by a controlled metered addition of hydrogen to Philip process, one can get LLDP as well as LLDP. So, Philip process can give both, it can give HDP, and Philip process with hydrogen can also give LLDP. And after this, there was a technological breakthrough in form of this unipole process which uses fluoride bed reactor, and then these can be used for producing both LLDP and HDP. So, this is a technological breakthrough from union carbide, where they have gone from conventional reactor to fluid bed reactor, a new technological development for producing this high molecular weight polyethylene. So, this shows the chemical reactivity space for from an industrial perspective for producing the various grades of polyethylene. So, what we can see that this low density polyethylene is the one which is produced by radical polymerization, whereas both LDP and LLDP they are produced by ionic or cationic coordination insertion polymerization. So, now we are going to move on to something more interesting, and that during the course of the development of all these Philip process and then Unipol process, there was a parallel development on Ziegler development towards Ziegler-Natta catalyst was taking place simultaneously, and the story all starts with this Aufbau reaction or chain growth reaction on aluminum, and so we are going to take a look at this exciting development as we proceed further in this lecture. Aufbau reaction. The Aufbau reaction is this reaction is primarily used for the formation of linear aliphatic compounds with a maximum chain length of C200. So, at that time this was a sort of polymerization on the back of aluminum Aufbau reaction, which is called chain growth reaction at the back of aluminum, and which could give linear aliphatic compound of maximum length of C200. So, that is really long chain compounds, and the reaction of this is given as R2Al ethyl N minus 1 CH2 at 90 to 120 degrees centigrade 100 bar gives R2Al CH2 N. Now, what is happening is these CH2 unit, it is getting added on this metal ethyl bond in high pressure, and this Aufbau reaction, this is what is called Aufbau reaction, and this reaction competes with another reaction called hydroalumination. Aufbau reaction competes with another reaction called hydroalumination. And this is given as R2 Al CH2 R dash, giving dehydroalumination, sorry, this is dehydroalumination. R2 Al H plus CH2 double bond CH R dash, and this can be explained as a beta hydride elimination and this is explained as such. So, one gets aluminum hydride and these alpha olefin. Now, these are really long chain products, long chain polymer. And Carl Ziegler was observing this formation of these long chain polymers in his laboratory during systematic study of Aufbau reaction Ziegler observed an opposite effect, that is quantitative conversion of ethylene to 1-butene quantitative. So, instead of observing very high polymer chain width, the Ziegler observed that in one cases he had observed quantitative conversion to just oligomerized product or dimerization of ethylene to 1-butene, and this was a surprising observation. And was later attributed to the presence of impurity in the reactor, and this is supposed to be nickel impurity, reactor, and that was later known as the famous nickel effect. While pursuing this off-bow reaction under different condition, carrying out a systematic study, Professor Carl Ziegler observed that in certain cases exactly opposite was happening, that is a quantitative conversion of ethylene instead of making polymer was making 1 butene, and this was sort of contrasting and surprising observation at the time of the study, where the focus of the off-bow reaction was to make long chain polymer, and here they were quantitatively getting dimer. So, this surprising observation was later attributed to the presence of impurities in the reactor, particularly the nickel impurities, and which was famous, which was later came to be known as the famous nickel effect, that actually triggered the discovery of Ziegler-Natta polymerization. So, with this I come to an end of today's lecture. In today's lecture we have looked at the various industrial processes that are prevalent or were prevalent in producing or accessing various kinds of polyethylene, ranging from LDPE, LLDPE and HDPE, and we had also put in a perspective various discoveries and changes that were affected on individual processes to access each of these polymers. We have also looked into the beginning or of Ziegler-Natta beginning of the discovery of the Ziegler-Natta catalysis, starting from off-bow reaction, and how the opposing effect of nickel impurities led to dimerization of ethylene to 1 butene. So, that was later recognized as the famous nickel effect, and which even triggered the discovery of Ziegler-Natta catalysis. So, with this I thank you for being with me in this lecture. We are going to be discussing further from the point of nickel effect to Ziegler-Natta and various type of other Ziegler-Natta catalyst examples as we take this topic up in the next class. Till that, thank you and goodbye.